inside of this lesson, we're going to take a look at how to factor higher degree polynomials. So these are polynomials that have a degree of 3 or higher. We're going to take a look at two different techniques. The first one we use when we have degree 3 and we have a special form. It's called factoring a sum or difference of cubes. And then after that, we're going to take a look at what's called the factor and the remainder theorem. Now we're in shape to talk about the first main theorem of this lesson. This theorem has a special name. It's called the remainder theorem. And it says if the polynomial p of x is divided by the linear factor x minus c, then the remainder after we do division by this linear factor x minus c is p evaluated at c. So what does this mean for us? It's quite a nice theorem if all we want to do is figure out the remainder of our polynomial division. If we're given a polynomial and we want to divide by x minus c, and we just really want to know what the remainder is, all we have to do is evaluate p at the number c. To see an example of the remainder theorem, let's take a look at the polynomial p of x is equal to x cubed minus 2x plus 5. And we want to figure out what the remainder of this polynomial is when we divide by the linear factor x minus 2. Now we do have some options. We could use long division or we could use synthetic division, but the idea of this lesson is to show you a more efficient way using the remainder theorem. The remainder theorem tells us if we want to figure out what the remainder is, all we have to do is evaluate p at 2. Well, what is p at 2? P at 2 is 2 cubed minus 2 times 2 plus 5. 8 minus 4 plus 5, or 9. So without having to do polynomial long division or synthetic division, we know the remainder is going to be 9. The remainder theorem in and of itself isn't really much of an important theorem, or it doesn't look like it on the surface. But let's take a look at this example to try to explain the importance of the remainder theorem. Let's take the polynomial x cubed minus 2x plus 4, and we're going to try to find the remainder after division by the linear factor x plus 2. To do this, the remainder theorem tells us we should evaluate p at negative 2. If we evaluate p at negative 2, we get negative 2 cubed minus 2 times negative 2 plus 4. Negative 2 cubed is negative 8. Negative 2 times negative 2 is 4. So p at negative 2 is actually equal to 0. What does this 0 tell us? Well, it tells us that there's no remainder if we take our original polynomial p of x and we divide by x plus 2. This is a really important idea, and it leads us to the next theorem. The factor theorem says the following. If we take our polynomial p of x and we evaluate it at c, and we get an answer of 0, then the polynomial p of x is evenly divisible by the linear factor x minus c. In other words, this is telling us that p of x has a factor x minus c. What the factor theorem really does for us is it gives us a strategy for factoring really large polynomials. Here's the idea. We guess at numbers, c, that we think are going to satisfy the following. P at c equals to 0. As soon as we find one of these numbers, then we can use either long division or synthetic division to factor p of x into two smaller polynomials, one being x minus c, and the other one having degree 1 less than our original polynomial. Now what we're hoping is that we'll eventually get down to a quadratic polynomial, and then we can factor up that polynomial using strategies that we already know. Now if we happen to get rid of the linear factor x minus c and we still have a really high degree polynomial left over, we can just repeat the process of the factor theorem until we get a small enough polynomial that we know how to factor. Let's use the factor theorem to factor the following polynomial. P of x is equal to x to the 4 minus 5x to the 3 minus 19x squared plus 29x plus 42. Now remember that the factor theorem says if we can find a number that we can substitute into our polynomial and we get the value of 0, that's going to be our candidate for polynomial long division or synthetic division. I like to pick some of the easier values first, so you'll see me often try to pick 1 and minus 1 and see if they work. So here, let's go ahead and evaluate p at 1 and p at minus 1 and see what happens. Well, p at 1 is going to give us 1 minus 5 minus 19 plus 29 plus 42, which is equal to 48. So p at 1 is not going to work for us. Next, let's try p at negative 1. Here, we're going to get negative 1 to the power of 4, which is positive 1, minus 5, negative 1 to the power of 3 is negative 1, minus 19, negative 1 squared is positive 1, plus 29 times negative 1, plus 42. So if we go ahead and simplify this, we'll get 1 plus 5 minus 19 minus 29 plus 42. And here we do in fact get 0. So this tells us that x plus 1 must be a factor of p of x. Now that we know the linear factor x plus 1 factors evenly into our original polynomial, we can use synthetic division to figure out what the remaining polynomial is going to be after we divide by x plus 1. So let's work through this synthetic division. So I'm going to bring down the 1. Negative 1 times 1 is negative 1. Add these two to get negative 6. Negative 1 times negative 6 is positive 6. Add this column to get negative 13. Negative 1 times negative 13 is 13. Add this column to get 42, and then negative 1 times 42 gives us negative 42 for a remainder of 0. If we try to divide our original polynomial by x plus 1, we're going to get the following other factor. So remember, this is remainder constant x squared, x cubed. So we get x cubed minus 6x squared minus 13x plus 42 as our other factor. Now, since this isn't something that we can factor readily, we can repeat the process of the factor theorem and synthetic division to factor this one more time. So here you have to play a little bit of a guessing game once more to get a factor. I happen to know that 2 is going to work, so I'll show that substitution for you. If we sub 2 into this polynomial, now this polynomial I'm going to call p of x. It's my new p of x. And if I sub in 2, I'm going to get 2 cubed, which is 8, minus 6 times 2 squared, which is 4, minus 13 times 2, plus 42. Okay, or 8 minus 24 minus 26 plus 42. And this should be equal to 0. So the factor theorem tells us that x minus 2 must be a factor of our new polynomial p of x. That means we can take the coefficients of p of x, and we can do synthetic division with the number 2. Bringing down our first one, we have 2 times 1 is 2. Negative 6 plus 2 is negative 4. 2 times negative 4 is negative 8. Adding these two together, we'll get negative 21, and then our final multiplication gives us negative 42 for a sum of 0. After this second synthetic division, we can now return back to our original therefore statement and factor this cubic once more. So we still have a linear factor of x plus 1. The factor theorem told us that x minus 2 is also a factor. And after we do synthetic division, we're going to have x squared minus 4x minus 21. And now we can finish up our factoring of this bigger polynomial by factoring this trinomial. So two numbers that multiply to give us negative 21 and add to minus 4 are the values of 3 and negative 7. Alright, my little epsilons, stay positive.